那我们第一场演讲将在这一个10点半的部分由这一个我们会开始哈。那第一场比较特殊哈，因为这个是由杜邦的这个微电路部门的首席研究科学家那个 Brian LAUGHLIN 的这个做这个部分。那我们等一下会进行一些简单的连线测试完之后，我再正式的去介绍这个讲者的部分。So let me to introduction the first speaker is Brian LAUGHLIN. Brian LAUGHLIN is a graduate from the North Carolina University. He have been major in ceramic and glass materials, and he have been working in the DuPont MCM department and to do some LTCC and silver paste research. And today the conference we are very honored to invite Dr. Brian to do the speaking. Their speaking topic is low temperature cold-fired ceramic for mmWave antenna in package. We are welcome Dr. Brian. Thank you.
Thank you, Dr. Liu. So first I'm going to say thank you for the invitation. I wish I could be there in person and have discussions with you directly, but in this world and this day, this is the best you can do. So over Teams or Zoom or over video chat. So thank you very much. So first, my agenda today, I want to start by just grounding everyone in what is low temperature co-fired ceramic technology. And through that discussion, I'll start talking about the DuPont green tape product lines 95C and 9KC. And then that'll culminate in what you've seen in the video already, what our AIP demonstration using our materials. And then I'll try and go a little bit further with some specialized applications and product features, and really what we think is the power of DuPont green tape LTCC for the telecommunications industry. So first, what is DuPont green tape LTCC? So it is a product that we sell. It's a dielectric ceramic tape that we sell in the unfired state. You can punch vias, fill them, screen print conductors or resistor traces in the XY plane, all in the unfired green state. You can then collate and laminate and co-fire the stack at what's a low temperature for ceramic processing. And what you get in the end is looks very similar to a printed circuit board cross section. Very similar to what a printed circuit board would look like, but instead of being made out of FR4 prepreg and epoxy, it's made out of ceramic as the dielectric inner layer. And we'll get into why there's a lot of advantages to using ceramic as a material for the dielectric opposed to polymers. And so it's a material that you can use to do everything that a printed circuit board can do, but there's also a lot of other things that you can do with it. It has been traditionally used as a ceramic chip package, and there are lots of components from LTCC capacitor components that are made of LTCC technology, all the way to where high quality antennas are often made on ceramic modules. But the power of using this LTCC in a green state and thinking about it as a module packaging material is you can take all of these ideas of components, put them, embed them in the package, use them as a chip packaging material, have an antenna layer, and assemble it all together as an antenna in package solution. Even after you make your ceramic module by the LTCC process, you can even do post-processing and put on surface mounts and computers to make a module. And we'll try and build into where you would get there. So that's the basis of what LTCC is in general. The process that we internally provide to the industry is a ceramic tape. And so here's just some references and figures for how you make this unfired ceramic tape. We start with our proprietary recipes and raw ingredients of ceramic powders, mix them with solvents, add binders and additives, make sure everything has high quality, and then put it in a doctor blading or slot coating type apparatus that is used pulling a mylar film under the wet slurry. And then that mylar film is then, that cast material on the mylar film is then driving off the majority of the solvent to leave a flexible piece of laminate material that has all of the ceramic precursors as well as some binder resin that keeps everything together. So that we provide in the process that we run prior to it being sold out in the industry. So what our customers do, or what the material we provide is used in the industry. Again, we're making green, meaning the unfired state. We sell typically in boxes or bags. And then, like I said before, you can punch vias in the precise place you want to be. Because this is a parallel process, you can run multiple punches at the same time, saving throughput. And you can do automatic inspection. If there's ever a defect at this point, you can throw that sheet away and replace it with the correct processed material. You can then do a via fill. You provide a place for that. I'll show that in a couple of minutes. Again, inspect to make sure there's no defects at this point. You can do the conductor print. That's then going to be the XY plane of all the circuits. And collate precisely all of the high quality layers that you've made for registry, and then go through the lamination step and the firing step. If you need to do post-printing or post-firing processing assembly steps, you can do that. And then in the end, you have your fully functional module that you can put through final test. So that's a high-level overview of the entire LTCC process. So the materials that we sell today, if you were to talk to someone about procuring a material, we have two main product lines that we'd like to present today. One is 95C. It's a lead-containing system, and 9KC, which is a lead-free system. And we'll sell it by increments of both the green tape thickness, so indicated by 200 microns, 165 microns, 125 microns, 150 microns, etc., in select sheet sizes, so usually 6 inch by 6 inch or 8 inch by 8 inch. And we sell it in a box, with 100 to 400 sheets per box. And so those are the product variants that we have set up today. If there's a high volume opportunity that requires something of a slightly different thickness or a slightly different sheet size to work into the process that you have, we are always open to have that discussion to explore if we can provide a variant if it makes sense. But that's the products that we have today. And then to talk about the design rules of what you can do with those products. So there's a whole list of design rules that have to do with how big of vias you can make and how close they're spaced together, and XY printing design rules. I'll leave these charts here that I'm sure will be provided as you need or on our website. But I'll say, if I kind of put it into generalities, we have tape thicknesses from about 50 microns to 200 microns. We can probably go thinner than that. We can definitely go thicker than that. Because the material shrinks on firing, that means that your design thickness is somewhere around 40 microns to 170 microns per dielectric layer. Our typical lines and spacing design rules are about 5 mils lines and spaces, or 125 microns. But again, because there's shrinkage, it's more like 100 microns. And I'll talk in a couple minutes about how that's the sort of widest, most general design rule. But the advanced processes, if you wanted to go with a lot of care and a little bit more expense in your screen printing or your patterning, you could get down to 50 micron line spaces, so something about 45 microns fiber. And again, I kind of show a cartoon cross-section of all the things that you can do, you know, in a cross-section view. So you can make internal lines that turn into capacitors because they're parallel, or you can make internal ground planes, or you can make internal signal routing. You can even put resistors on the top and have an overglaze to environmental protection. You can make thermal vias, and you can make cavities for ease of wire bonding for chip carriers. And so all of those design rules, we will publish a set of design rules, are probably the most general. To a foundry, they probably have their own design rules that may be slightly more aggressive than something we might provide, which is an overview of the entire industry. But this is the sort of length scale that we're talking about. I would say it's on the size of mills. It's on the size of about 25 microns, 50 microns, 100 microns. That's kind of the length scale we're talking about with LTCC. And then we provide paste for all kinds of situations. So there's a specific type of paste for filling vias. There's a particular type of paste for making a ground plane versus a signal line, signal line internal versus signal line external. And then we will have different, usually alloys or mixed metal compositions for if you need to do the assembly later of solderable or doing overglazes or brazing. And so you can talk to our advanced engineering field support for selecting the right paste for the build that you need to make. But when we say a green tape 95C, it's a full family system of the ceramic tape and all of the pastes that you would require to make a fully functional circuit or module. So like I said, design rules in the most general sense, we kind of talk about it on 5 mil length. And that's what I kind of put here on the left side. If you were to just do traditional thick film screen printing, it's a very low cost, high volume, established industry to do that kind of screen printing. It's relatively simple screen print and fire, so it fits well into the co-firing step of LTCC. There are more expensive, more advanced screens you can have, very sophisticated printers, make some possibly sacrifices in the speed and throughput of the printing step to where maybe you could get 75 or 50 micron lines and spaces. But then the firing process is relatively the same. It's still, I would call it low cost and high volume because it's still a screen printing operation. The advantage of LTCC for the via portion, we can get down to something that's 1-to-1 aspect ratio to the film thickness. So that means as small as, 2, 3, 4 mil vias, and then as big as, 100 or 200 micron size vias. And here, it's sort of a subtractive process from the dielectric standpoint, but additive from the metallization paste. And so there's just an extra process step of punching the via in the ceramic and then doing the via fill and fire. And this all is meant to co-fire with the other screen printing XY direction paste. We have other variants that you could use. We have something called diffusion patterning paste, something that you print and then we'll use an aqueous develop after imaging and then fire. That's somewhat of an additive print subtractive via process. We have Fodel paste that we've used in the industry, which are photo imageable. Again, you would print something slightly bigger than what you want, use photo imaging and then aqueous develop before firing. And then there's even more advanced processes where you could use a laser to laser ablate the edges of your lines or to cut up smaller blocks into individual lines. Then that could be before a fire step, but usually after the firing step. That has the advantage of being no chemistry, but you need a sophisticated laser to use it. And then if you really needed the most high density circuits, you can still go to a photolithography method. So you would do your screen printing or whatever metal deposition, do some firing step, and then you would use photoresist, probably like a dry photoresist like Riston, do photo image develop, and then use a wet etch chemistry to etch back what you don't want. And so you can go from a low-cost, high-volume situation of being at 100 micron length scale to taking the most expensive, the most care, and going as low as, possibly 10 micron length scale. So when we say there's design rules, it's usually based on this more traditional thick film screen printing. It would be at your decision to go to the more expensive technologies later. So I want to go through some of the important steps of LTCC because they have an implication for your success of making a build. So after you do all of your via punching and via filling and screen printing, and you collate all of your layers together, the lamination is an important step. So because of the way we cast the film, there's a machine direction and transverse direction. And you need to take care to not only collate your parts, but to make sure you alternately assign the different directions of the machine direction and transverse direction. And so we put a dot on the sheets for what direction the tape was cast at. But because you get it in the green state, and there is somewhat of amount of resin left, you laminate at about 70 C, which is above the TG of the resin. That allows there to be a little bit of plastic flow and some tacking of the layers to each other in a relatively high lamination step, so 3,000 to 4,000 PSI. And so once you get out of that, it's still unfired, it's on its green state, but all the layers take on a tack and the registration that you have carefully put in there. And there's some ability to change the green to fire shrinkage by the lamination pressure. 9.5C particularly has a wide process window where you can use this lamination pressure to change the shrinkage by a couple tenths of a percent. But really the part where most of the process design complexity comes out is in the firing step. So I'm going to take a minute or several minutes to talk through the firing step. So this is called low temperature co-fired ceramic. It's very high temperature if you compare it to a organic laminate printed circuit board type of construction, which is just an autoclave at 180 C. Here we're firing at 800 to 900 degrees C. But we call it low to differentiate from its high temperature co-fired ceramic variant, where you're actually sintering ceramic particles without glass. And that's usually something more like 1200 degrees to 2000 degrees C. The reason this is an important distinction is not just because of the energy input for lower temperature firing, but in HTCC, you are above the melting point of high conductivity metal traces. And so usually you're restricted to something like tungsten or molybdenum as your conductor material, which has particularly poor conductivity compared to things like gold or silver or copper. The low temperature co-firing, because there's a glass-aided sintering of the ceramic, we're below the melting point of gold and silver. So you can use those very high conductivity, high reliability materials. We tend to focus on gold and silver because they are noble metals and can be fired in air. There are ways to design processes to utilize copper metallization, but it takes nitrogen firing, which is not a common thing to have in an LTCC shop. All of that firing and the design of the tape and all of the conductors are all formulated together for compatibility, not just chemically, but in the way they all sinter. And so the conductive inks are formulated and matched to the particular product lines so that the conductor pattern will shrink simultaneously and in the same degree with the dielectric tape. So in your design, you're restricting what you think you put in doesn't get distorted and disturbed in the co-firing sense. And so mixing and matching other providers' conductors with our tape is not recommended because things will shrink differentially and cause lots of mechanical and distortion issues. But because you can do this co-firing step, not only do you make a 3D construction, but you save time on what's the more lengthy process of firing, which can be, most of a shift or over multiple shifts to fire very large parts. And so the co-firing actually makes quite a big step for making this an economical process. You can batch fire lots of things at the same time. You're co-firing multiple prints at the same time. And so it makes it that's a critical economic step of co-firing. So to go through what a typical firing profile here is, and you'll see this over the next couple slides, usually a typical firing profile, you put it in either in a box furnace or a belt, you start at low temperature, and in the beginning parts of firing, you're going to heat relatively slow up to a shelf. And that's really to do all the pyrolysis and decomposition of the resins and to get all of those out of the system. Not only do you need to reach high enough temperature to decompose the resins, but you also, on a thick part, have to diffuse out those volatile decomposition products, water, CO2, CO, those kind of things may need to travel, millimeters through a part on the interior. And so that's why we have a shelf there. And so usually that 400 to 500 degree hold, it's below the point where the glasses soften and the actual ceramic starts maturing, but high enough that you will burn out and have high diffusion of all those organic construction. Because the glass hasn't started flowing, the system is still porous and open, and so it's quicker to fuse everything out and get everything out from the center. If you don't hold for a long enough period of time, you can trap all those hydrocarbon decomposition products, and will cause things like blips or delamination or even discoloring of the part because you have graphitization of those decomposition products that are trapped. And then you get into the ramp up to the final temperature. And so depending on the system, 9.5C has a pretty wide process window and a lot of latitude to change the heating rate in this ramp up. But in here is when you hit the TG of the glasses and sintering starts occurring, and you're going to start creating the microstructure that's the high quality dielectric that you want in the end. 9KC is a very high performance material, but has much more restriction on the heating rate in this final ramp. And then you reach a maximum temperature where you are really just trying to get all of the inorganic reactions to go to completion and densify the system as much as possible. So usually that's about 850. You can probably fire a little bit lower. It may be advantageous to fire a little bit hotter. Then comes in the design of your process for what you need the conductors to sinter to, what you need the dielectric constant to be, what you need the dielectric loss to be. A lot of that's happening for where you set the height of the temperature of the shelf and the length of this shelf. And so just as an example, a lot of this data came out of Tree's lab, Dr. Liu's lab. I would say there's two stories on this chart. So I show 9KC under different firing temperatures and firing lengths. So normally what we recommend is 850, 20 minutes, and you get what you'll see is the data sheet properties of DK and DF. And they're very, very good properties and very stable over a long frequency regime. But when you change the process, maybe even to extreme, from going from 20 minutes to 3 hours of a hold, you might change the dielectric constant a slight degree, or improve the dielectric loss a small increment. I would say you have this latitude to try and tune the process and balance the economics of your process versus the performance you want. But if you have process latitude and process variation on the scale of you don't hit 20 minutes exactly, it goes to 18 and a half, 21 minutes, or you're not at 850 exactly all the way through the whole zone of your furnace, you might be 10 degrees, 5 degrees off here or there, you're not going to see huge process variation shifts. And so you should keep really good yield because it's pretty stable in repeatability. And we're quite proud of the fact that we provide a product that has very high quality, that from lot to lot, sheet to sheet, box to box, has good repeatability in a practical firing process that has natural variability. And then the final step, it's usually not particularly critical as long as you don't cool too fast. So you do have a ceramic material at the end. probably coming from the high temperature state. You need to cool relatively gently up to some point so you don't thermally shock and cause, micro cracking or even massive mechanical failure of your part. So you have to avoid thermal shock. So the cooling still needs to be considered in your full firing process. So really, I take a lot of care to talk about the firing process because that's when you take in the most care to put all your printing together and where you're really going to develop the electrical performance of your entire device. And so we publish recommended profiles as a starting point, but it's all dependent on the size of your part, the complexity of your part, and what you need to balance in the economics and the variability of your process to get the necessary yield of what you want. One other concept that is a mix of design and process, because it shrinks from the green state to the fire state, and although we make all of our best attempts to make exactly sintering rate matched materials, in the end it's a balance between electrical performance and mechanical stability. And so there is a slight difference between conductor tray shrinkage and the ceramic shrinkage, and I think you'll see that in any LTCC process or set of materials. And so when you design a part, it's important to think about the symmetry of your conductor designs. And we often see people put non-electrically functional metal patches in areas just to balance the metal, because if you have a very asymmetric part left to right in the XY plane or even top to bottom in the Z direction, that would cause warpage of the final part. And so if you can, the best you can, make your device function, but also think about balancing the metal on the front and the back side to minimize the amount of distortion, warpage, or camber that you would create by an asymmetric design. So in the end, I want to start transferring from LTCC process in general to our specific material systems. And so I made allusion to it before. We have 9.5C and we have 9KC. 9.5C is lead containing, 9KC is lead free. They have different dielectric performance and material performance, and they're suited for different things. So 9.5C has a slightly higher dielectric constant of 7.5, and it has a loss of about 0.006 at about 3 gigahertz. Contrast that with 9KC, which is a slightly lower dielectric constant, but really where 9KC really shines is a very low dielectric loss. So on this data table, 0.001 at 10 gigahertz, which is kind of our QA level. And I'll show a more frequency graph in a moment. They both go through shrinkage. They're chemically different systems. The shrinkage is slightly different, and therefore the paste that go with them have to be their own specific family of paste. But they're repeatable with about 0.3% shrinkage from sheet to sheet, box to box, lot to lot. And so you can rely on those kind of numbers. And I mentioned before that 9.5C, you can change it by a couple tenths just by lamination pressure. Beyond electrical performance and firing performance, the thermal expansion coefficient of LTCC in general and for these two systems are well matched to semiconductors. I'll show in a couple of minutes about how organic laminates struggle to get that kind of match of thermal expansion coefficient. And then thermal conductivity is quite high because it's a ceramic material. And 9KC is a particularly high, 5 watts per meter Kelvin thermal conductivity through just the dielectric, before you consider the fact that you can make metal plugs and thermal vias. And then there's ceramic materials. They're known to be, they brittlely fracture, but that doesn't mean they're weak. So they have high flexural strength when they're fired and fully mature. Yes, when they break somewhat catastrophically, which is different than a plastic board, but they're quite strong and they have high fracture toughness. And because they're dielectric materials and fully dense, they have very high breakdown voltage. And so for a power module, they can take quite a bit of current abuse temperature. And so that makes LTCC a very high reliability technology. And these particular material systems, some of the best out there for all of the holistic need of a module, not just the electrical design, but the mechanical and thermal design. So looking at specifically the dielectric constant, the dielectric loss, on the left you see 9K. 9.5C, good frequency stability for decay. But if you look at the dielectric loss, it stays relatively stable, but it's in this 0.006 range. And that's quite high once you start thinking about high frequency design. So we recommend 9kc for situations and devices that operate less than about 20 gigahertz. But if you have a really high frequency, high performance design, we recommend 9kc. So again, the dielectric constant is very stable over a large frequency regime, and the dielectric loss is 6 times better. And it's a very good dielectric loss that stays low even up through high frequency. And just to even drive that point further with 9kc, if we go through even a wider temperature analysis, or frequency analysis, sorry, you can see on the left, the loss tangent stays below 0.001 all the way through up 100 gigahertz. And the dielectric constant is stable through that whole regime. And so this is a quote we've heard, not something we've created ourselves, but this is the lowest microwave dielectric loss, LTCC, commercially available that you can buy on the market. And we're quite proud. I think this is a very excellent material for high frequency designs. And that's a very important concept because 5G is moving into this millimeter wave high frequency regime right now, and will only go to higher frequencies in 6G. Not only do you get that great dielectric constant, dielectric loss performance versus frequency, but it also is stable over ambient use conditions. So here's applied 28 and 38 gigahertz for 9kc, where we show the dielectric loss tangent and dielectric constant from minus 50 degrees, 150 degrees measured in situ. And here you see almost no change in the dielectric properties over the practical use conditions. And it's a little bit difficult to have a data plot in here. LTCC is inherently impervious to moisture. So it's a dense microstructure. There's no chance for there to be any shift with material properties with humidity or water absorption, unlike a lot of polymer materials that you could use that are not in kind. And so that makes LTCC not only good at the base design, but in the in-use situation, it's also a very good material. And so I want to kind of contrast it to what else you could choose besides our 9.5C or 9kc LTCC material. And so there's a lot of data on this chart. So I put here green tape 9.5C, 9kc. Some of it is repeated here. I put the process temperature. You can go above 100 layers if you want to in LTCC. Most practical modules are something between 4 and 12 layers. Dielectric constant, loss, shrinkage, everything you've seen before. Surface roughness is quite important. Once you get to high frequency, skin depth causes conductors to look like they're more resistive than they really are at DC. So we're still in the sub-micron range of ceramic surface roughness. And then even the conductors inside usually either take on the surface roughness or might be slightly better through the lamination step. And the same things with the thermal properties that we showed before. I contrast that with if you just did thick film printing on alumina. Here the firing temperature is the same, but if you were to just print a conductor and then a dielectric crossover and another conductor, after you add up about 5 to 7 layers, you reach a real planarity problem, and it's difficult to design a device, simulate a device that's very non-planar. There's a lot more latitude to have different dielectric constants there, but your loss isn't necessarily going to be better. We try to do the best we can to make good thick film dielectrics, but LTCC 9kc is just a bar that we cannot reach that way. There's not really any shrinkage in thick film on alumina. There is in the Z direction, but not in the XY, so it makes that slightly easier. And you can process things on like aluminum nitride that has very good thermal conductivity. If you wanted to. It's a little bit more difficult. It takes nitrogen firing, a little bit more care. But you could do thick film and alumina, but you're not going to be a planar device. And then I also put on here what's the ubiquitous material, which is pre-preg epoxy FR4. So here you're processing much lower temperatures. You still have a multi-layer capability. The dielectric constant is typically a little bit lower just because organics have a lower dielectric constant than ceramic and organic materials, but the dielectric loss is an order of magnitude or more worse. And so printed circuit boards are great because they're cheap and ubiquitous and easy to access, but they're not going to make good high frequency designs that give high efficiency devices. Many of the other properties are relatively similar. PCB, you may sacrifice a little bit on insulation resistance. Maybe the breakdown voltage is okay, but in some situations it might be much worse. But the thermal properties are really where PCB looks a lot worse. And so if you have high power designs or high density designs, one, the thermal expansion coefficient for a printed circuit board, to keep its mechanical reliability, the organics usually match to the copper inner layers. So that's about 17 ppm. And so it makes it quite a challenge to assemble the semiconductor chips on top and go through all the reliability testing or the end-use testing without having assembly failures. And then the organic part of the printed circuit board has an order of magnitude lower thermal conductivity than any ceramic material would have. There are constructions that are just as strong. They're a little bit more flexible or have some give, which is different than ceramic. In the end, they have about the same mechanical properties. But really, this thermal and this higher dielectric loss really makes printed circuit boards have a lot of difficulty in designing practical devices at really high frequencies. And so I kind of make that statement up here. The radar plot also kind of shows a lot of the same thing where we contrast either printed circuit boards or advanced printed circuit boards that are based on fluorinated Teflon-like materials or even liquid crystal polymer. Really, those have advantages. LCP is more flexible. PCB is more ubiquitous and there's more installed capacity for processing, and so it tends to be somewhat lower cost because of its economy of scale. But a lot of the other things, LTCC is hermetic, it's stronger, has much easier thermal management design. Because of the higher dielectric constant, you might be able to get higher circuit densities without having a thermal problem. We have a really good thermal expansion coefficient match to the semiconductor devices that are powering the circuits. LTCC is well known for being a very high reliability material because of all the other properties we talked about before. Dielectric constant can make something smaller, so the footprint can smaller and the weight can be smaller. And so it looks really good. LTCC looks very attractive from a radar plot perspective. And then the last point, I'm going to kind of harp on this and repeat this over and over again. The thermal conductivity comparisons of the DuPont green tape at about 4.6 is better than LCP and an order of magnitude better than any of the polymer solutions. So even ceramic fill, PTFE, is still an order of magnitude lower. FR4 is 1.5 orders of magnitude lower. Unfilled PTFE is the same as FR4. Polyimide might be even worse than that. And so, yes, you can design a really very high performance device. In operation, you can get the heat out. Very long, you're going to have early failures or field failures. None of those things are going to make a practical situation. And then really, I've talked a lot from the material perspective and been somewhat alluding to the design and the practicality of using LTCC as a material. But in our attempt to really prove to the industry that our LTCC really can do all these things that we're hypothesizing. We work with Dr. Liu's lab to use 9Kc silver metallization to make this module that you see here, which is a 2x2 antenna array on one side, and the ability to mount a mmWave phaser chips on the back side with all the surface mount requirements to make a functional antenna and package module that operates at 28 gigahertz. And so here I show a picture of it fully assembled on the chip side. Here's a kind of cartoon schematic of what in theory looks like from the middle. So you have your chips then routed through surface mounts or embedded passive signal conditioning, power dividers to the antenna layer that's on the bottom. And then on the left, you can see those antenna or radiating elements match exactly from the simulated design state to the actual measured state. And when you put in the mmWave chips and a full system to drive the mmWave chips to use their phaser capability, you can do beam steering minus 35 to plus 35 degrees with ERT up above 18 dBm. And so we utilize the fact that there's very, very low dielectric loss and the ability of our 9KC to make a fully integrated system to make not only a very high quality antenna package beam steering array, but if you look at the error vector magnitude measurement, so when you do the 64 QAM and look for your error data rate, we're below 1% data rate. Actually, it's measured in parts per million here as what our data rate is. And so not only are we getting really good antenna performance from just an over-the-air radiation pattern, but we can transmit data reliably to the level that we built a full system where we can transmit 4K video over 10 meters continuously, where the main transmitter is this fully integrated module made out of DuPont green tape 9KC system as being the main transmitter. And so we hope this reference design, proves our hypothesis that not only is LTCC a really good material, but it makes a very practical, high quality device that's highly reliable. And so we're quite proud of this effort. I hope you help us there today. I hope you get to see it today. The video talked through this in more detail that you saw this morning. Just a couple more things that I wanted to comment about. So we have design rules for making cavities. This is actually a very old way to think about using LTCC. And so I just have a reference from a paper that I found here that's quite old, where you can use LTCC simply as a high-quality chip package. To do that, you usually put the chip recessed into a terrace, kind of like a lead frame construction. That minimizes your wire bonding length and makes it easier to do the wire bonding and the assembly. But LTCC is well suited for making lots of cavity designs for whatever you need cavities for, but most times it's for chip packaging. And so there are design guides, and you can make cavities on the scale of millimeters in a part. You can't, and so here there's information about that design rule. And then more recently, one of our customer partners, Centec, has shown how we can make buried cavities. And so through their process, they can make 8 millimeter wide, half millimeter tall buried cavities that are not even open to the air. And this is quite an attractive concept because when you design an antenna and you operate an antenna, the ideal dielectric constant is air, dk of 1. And so you can put these buried cavities under the antenna layer to simulate a much lower dielectric constant under the antenna layer, but still use the high dielectric constant for all your signal routing and assembly, and use that miniaturization on the other side where you're doing all your circuitry and your circuits. And so it's just proof of how extendable and how complex of a design you can make using LTCC. And so I'm going to start wrapping up here. So not only is LTCC a really good material for making very excellent circuits, but doing the circuit design or the module design or the system design, flexibility. So one, you get superior dielectric thermal conductivity and thermal expansion coefficient that matches to the ICs, which are usually the most expensive component that you're putting in your device. And that really simplifies the thermal design or minimizes the chance of an error or oversight. And then because you have ultra low dielectric, very stable performance, you have a lot more latitude to make a high quality circuit. I know there's ways to do design in high poor dielectric materials, but if you don't need to go through those compromises, it opens up much more design space for you to make a design for what you need. And If you need different dielectric constant, you can put cavities in the design or use something like lead frames to manipulate locally what the dielectric constant looks like on the circuit. And then because you do this co-firing and you have the opportunity for parallel processing with inspections where you can take out lead yield detractors midpoint of the process when it's cheap, all of that makes the potential for a very economical process that can have really high yield out of the end of the LTCC fabrication. And so you can pick out a lot of the defects early when it's less costly to fix them, and so you get really high yield of your device at the end in manufacturing. So really, the reason we're here and I'm here talking through all these details is we want DuPont microcircuit and component materials with DuPont MCM green tape LTCC to be your partner when you're trying to make mmWave 5G. We think LTCC is a total solution. We understand our materials well, you understand your device needs well. We would like to hear about your designs. We would like to work on your designs and give you a lower cost, higher performance total solution using DuPont green tape. So thank you all for your attention. There's not any question and answer here today, but I'd be more than happy to field any that are available. So thank you.
Okay, thank you, Brian. 那我们现场可以，因为他还有大概5分钟的时间哈，那如果现场有要提问的，我们可以提问。好，那提问的话，那个现场前面有麦克风哦，所以你可以按钮然后讲。那请问一下，现场有没有什么样的问题需要跟这个 Dr. Brian 去做一些询问？ OK， 没有。那这个，那 Thank you Brian, and very appreciate your speaking presentation. Thank you.